than I can. Okay, chemistry 1411. Before we get into electrochemistry in detail, which we're going to do in the next lecture, I just wanted to review oxidation numbers with all of you quickly. This is a concept that you would have seen in General Chemistry 1. But again, I just want to take a quick peek at it here with you before we really get into looking at redox reactions, where we have to evaluate oxidation numbers pretty quickly. So we'll start slow, and then we'll see how quick we can get, okay, how fast we can get on our oxidation number. So what is an oxidation number? If you're wondering what the heck's an oxidation number, if you look at a compound like sodium chloride, it's an ionic compound, you know that the sodium has a +1 charge and that the chloride has a -1 charge. Those are the oxidation numbers. So sodium has an oxidation number of +1, chlorine is -1. But if you look at a compound like CO2, carbon dioxide, that's a covalent compound. It might not be as abundantly clear what the oxidation numbers are there because it's not an ionic compound. It's not as simple. We don't think about those elements as being ions. So in order to determine oxidation numbers, we use a bunch of rules to determine them. And what are these rules based on? They're based on the idea that the oxidation numbers represent the supposed charge on each atom in a covalent molecule or an ion. So in an ionic compound, it's a lot simpler because you're used to looking at ionic compounds that are comprised of a metal and a non-metal. When you look at a compound like carbon dioxide, it's not as abundantly clear, but this is what we base it off of. We base it off of the fact that the electrons are going to be assigned to the more electronegative element, right? You should know that the trend in electronegativity is that as we proceed upwards and to the right in the periodic table, the electronegativity increases. In fact, oxygen is the second most electronegative element in the periodic table, and it is more electronegative than carbon. So we're going to assume that it's hogging all of the electrons in the bonds in that molecule. Okay, so we assume that even though we have a covalent compound, we treat it as if it's an ionic compound. And if it's an ionic compound like sodium chloride, then electrons are totally transferred anyway. Let me show you the rules, then we'll take a look at a couple of practice problems. If you have a free element, so any element that's in its uncombined standard state, hydrogen, bromine, sodium, beryllium, whatever we have here, they have an oxidation state of 0. And you have to know what the diatomic elements are, right? Brinkelhoff or have no fear of ice cold beer, however you remember it, you need to know hydrogen, nitrogen, bromine, chlorine, oxygen, fluorine, iodine. You need to know that those are the diatomic elements. You should also be aware of phosphorus comes in packets of 4 and sulfur comes in packets of 8. And all the rest are just, monatomic. So those all have an oxidation state of 0, so no charge. If you have a monatomic ion, well, that's also pretty easy. And I don't like to use the word easy in chemistry class a whole lot. So basically, if you have a lithium with a +1 charge, it's got an oxidation state of +1. If you've got a barium 2+ ion, it's got an oxidation state of 2+. If you've got an iron 3+, it's got a charge of 3+. If you've got an iodide with a -1 charge, it's -1, so on and so forth. Okay, there we go. Any group 1A metal has a charge of +1. Any group 2A has got a charge of +2. Aluminum is always +3 in any compounds. Oxidation number of oxygen, it's almost always 2-. Okay, oxygen is almost this. It almost always has an oxidation number of 2-, except for in compounds like hydrogen peroxide, where it has an oxidation state of -1. So I'd say that hydrogen peroxide is a good example that, or a good exception that you should have in your head or memorized. Number 4, hydrogen is always going to be +1 unless it's combined with a metal. Right? It's always +1 unless it's combined with a metal, in which case it's called a hydride, right? When you have hydrogen with a -1 charge, that's called a hydride. Okay, so if you have, again, hydrogen combined with a metal, like lithium, sodium, calcium, that's lithium hydride, sodium hydride, and calcium hydride. So then it's got a charge of -1. Every other case, it's +1. Here's a really easy rule. Fluorine is always -1. There is 0 exceptions to that. There aren't a whole lot of rules in chemistry that there aren't exceptions to, or at least it feels that way sometimes. But here's one you can hitch your wagon to. Fluorine is always -1. The other halogens are almost always going to be -1. unless they're combined with oxygen in oxyacids, then they can have positive oxidation numbers. And we'll look at examples of that. In fact, I have one in the next slide, I think. A neutral molecule, the sum of all the oxidation numbers has to be 0. Okay, so let's say we were doing something like carbon dioxide that we looked at before, CO2. You can assume that the oxygen has an oxidation state of -2. How many oxygens are there? There's 2. So overall from the oxygen, I'm getting -4. All right, from my oxygen, I'm getting a total charge of -4. Well, the overall charge of CO2 is 0. So that means that my carbon must be +4 in order to balance that out. Okay, so that's the kind of strategy that we take. Well, with that in mind, let's look at some examples quickly because we're running out of time here today. We'll start with CCl4. That's carbon tetrachloride. Chlorine is a halogen. The halogens, like fluorine, chlorine, bromine, and iodine, they normally have a charge of -1 unless they're combined with an oxygen. There is no oxygen here. Well, how many chlorines do I have? I have -1, but I have 4 of them. That means I have a total of -4 coming from the chlorines. What charge must my carbon have in order to balance out -4 and give me 0, right? What I'm asking is -4 plus something gives you 0. What would that something be? It would be +4. And so the carbon is +4 and the chlorine is -1. Give me a thumbs up if this, jogs your memory to some extent. Anyone? All right, thanks, Joel. Well, and I'm getting lots of thumbs ups. Okay. Well, with that in mind, I want to give you a tough one. And when I say tough, I mean just a little more complicated than that one. This is the dichromate ion, Cr2O7 2-. Could anybody tell me what the oxidation state of the chromium is in dichromate? I'll give you a second to think about it, and then I'll answer it, and then we'll call it a day. Anybody can tell me what the oxidation state of the chromium is in dichromate? Yeah, heck yeah. Awesome. Stephen and Jamil, you're both 100% correct. It's +6. Okay, it's +6 and the oxygen is -2. How did those guys figure that out so quick? Let me show you what they did. They said the oxygen is always -2 unless it's combined in something like hydrogen peroxide. So we have -2 and we have 7 oxygens. So -2 times 7 gives me -14. Well, overall, the charge of this polyatomic molecule, or ion rather, is -2. So that means that -14 from the oxygens plus something gives you -2 for the whole damn molecule, right? And that something is going to come from the chromium. Well, the answer to that something is +12. So that means that overall from the chromium, I have +12. But that +12, I have to divide by 2 because there's 2 chromiums. So each chromium is going to contribute +6. So to summarize, my chromium is +6 and my oxygen is -2.